In this video, I'm going to be proving the integral test for you. And the integral test says that a series converges if and only if the corresponding improper integral converges. And I'm going to show you both directions of this proof. So the first direction, I'm going to suppose the improper integral diverges. And then I'm going to show you that the series must also diverge. Okay? So if the improper integral diverges, then I know that this amount of area that I'm going to shade in yellow, I know that's an infinite amount of area in yellow if the integral from 1 to infinity of f of x dx diverges. But I'm going to propose that the series is actually larger than the integral. Okay, right? We know that the sum of an is, or really the sum of f of n, as n runs from 1 to infinity, is going to equal f of 1 plus f of 2 and f of 3 and so on, right? Okay, but I could say, all right, that's this height plus this height and that height, and just keeping on adding these heights. But that doesn't really help. I don't have anything to like visually compare this to. Okay, so what I'm going to do, I want to compare areas to areas. So if I just gave this a width of 1 and turned it into a rectangle, okay, the sum of these red rectangles would represent the value of the series. They're some of the areas of these red rectangles, right? And you can see that necessarily it's going to be the case that the area inside the red rectangles is greater than the yellow area. Meaning the sum from 1 to infinity of f of n is greater than the integral from 1 to infinity of f of x dx. And we already know that integral went to infinity, so the sum is bigger than infinity, which is to say that the series diverges. Right? Now, suppose the improper integral converges. Suppose that there's a finite amount of area underneath the graph of f between x equals 1 and, well, to the right of x equals 1. Okay. Now, for comparison, I'm going to actually start thinking about the sum from n equals 2 up to infinity of f of n. Okay. And a different sum, but it'll be the same idea. It'll be f of 2 plus f of 3 plus f of 4 and f of 5 and f of 6 and so on, right? But if I wanted to get some area to compare this with, I might just go back the other way, right? Okay. And then I'm going to just make out some rectangles. And I think you see the point here. That last rectangle is pretty bad. Okay, so that's going to equal, f of 2 plus f of 3 and f of 4 and so on. But in this case, I can see that the series adds up to something less than the integral. Okay, now I know the integral converges to L, so this tells me that the sum from 2 to infinity of f of n must converge. Okay, and knowing that, I can say that the sum from n equals 1 to infinity of f of n is equal to the sum from 2 to infinity of f of n plus, well, just f of 1, right? If I kind of block that off like that. Okay. And I know that this thing that I've blocked off that I'm going to highlight in gray right here, I know that this series converges. F of 1 is going to be a finite value, so that the sum from 1 to infinity of f of n must also converge. Okay, so that's the other direction. And that's it. I've shown you that if the integral diverges, then the series diverges. And if the integral converges, then the series also converges. And that's the integral test, right? That if we need to know what's going to happen with an infinite series, we can check the corresponding improper integral, and it will uniquely determine whether or not the series is converging or diverging. So thanks for watching.